Quantum computers, the future of computing. Quantum computers represent one of the most revolutionary technologies of the 21st century, promising to change the way humanity processes information, solves complex problems, and understands the universe. Unlike classical computers, which have been the backbone of modern technology for decades, quantum computers operate on fundamentally different principles rooted in quantum mechanics. To understand why quantum computers are so unique and potentially transformative, we need to explore their history, the key differences from traditional computers, their unique properties, and what they could offer humanity in the near future. A brief history of quantum computing. The idea of quantum computing is not as old as classical computers, but it has roots in theoretical physics that go back several decades. In 1980, physicist Paul Benioff proposed a model of a quantum mechanical Turing machine, suggesting that the laws of quantum mechanics could be used to perform computations. Around the same time, Richard Feynman and David Deutsch independently suggested that classical computers might struggle to simulate quantum systems efficiently, and that a computer based on quantum principles could handle such tasks naturally. It wasn't until the mid-1990s that quantum computing began to move from theory to practical possibility. In 1994, Peter Shor, a mathematician at AT&T, developed a quantum algorithm capable of factoring large numbers exponentially faster than classical algorithms. This breakthrough demonstrated the real-world potential of quantum computers, particularly for cryptography. Shortly after, Love Grover introduced a quantum search algorithm that could search databases more efficiently than any classical counterpart. These developments triggered a surge of interest from both academia and industry. Classical computers versus quantum computers. To appreciate the uniqueness of quantum computers, it is important to first understand how classical computers work. Classical computers, like the laptop or smartphone in front of you, operate using bits, the basic unit of information that can be either 0 or 1. Every calculation, program, or digital operation boils down to combinations of these zeros and ones. The power of a classical computer depends on the number of bits it has and the speed at which it can process them. Quantum computers, on the other hand, use quantum bits or qubits. Unlike classical bits, a qubit can exist in a state of 0, 1, or both simultaneously due to a property called superposition. This allows a quantum computer to perform many calculations at once, potentially solving complex problems far faster than classical computers can. Additionally, qubits can be entangled, meaning the state of one qubit is directly connected to the state of another, even if they are far apart. This phenomenon allows quantum computers to process interconnected data in ways that classical computers simply cannot. To put it simply, while a classical computer checks one solution at a time, a quantum computer can explore multiple solutions simultaneously. This difference is not just a step forward, it is a fundamentally new way of computing, opening doors to possibilities that were previously unimaginable. Unique properties of quantum computers. Several properties make quantum computers extraordinary. 1. Superposition. As mentioned, a qubit can exist in multiple states at once. This allows a quantum computer to explore a vast number of possibilities simultaneously, exponentially increasing its processing power for certain tasks. 2. Entanglement. This is a quantum link between qubits that enables instantaneous correlations. Entanglement allows quantum computers to coordinate information between qubits in ways classical computers cannot, enabling faster and more complex computations. 3. Quantum interference. Quantum computers can manipulate the probability amplitudes of qubits, reinforcing correct answers and cancelling out wrong ones. This property is critical for algorithms like Shor's and Grover's, which rely on interference patterns to find solutions efficiently. 4. Parallelism. Thanks to superposition, a quantum computer can perform multiple calculations simultaneously, making it potentially millions of times faster than classical computers for certain tasks. 5. Quantum tunneling. Some quantum computers, like those built with quantum annealing methods, can exploit tunneling to escape local traps in optimization problems, finding solutions more efficiently than classical computers. Interesting facts about quantum computers. 1. Not just faster, but different. Quantum computers are not simply faster versions of classical computers. For most everyday tasks, like word processing or browsing the internet, classical computers are still more practical. Quantum computers excel in specialized tasks such as cryptography, complex simulations, and optimization problems. They are fragile. Qubits are extremely sensitive to their environment. Even tiny disturbances like temperature changes or electromagnetic noise can disrupt calculations, a problem known as quantum decoherence. Researchers are developing error-correcting codes to stabilize quantum computations. 3. Quantum supremacy. In 2019, Google announced that its quantum processor, Sycamore, had achieved quantum supremacy, performing a task in 200 seconds that would take the world's fastest classical supercomputer 10,000 years to complete. While this was a narrow demonstration, it showcased the potential of quantum computing. 4. Several approaches. Quantum computers are being built using various technologies, including superconducting circuits, trapped ions, photonics, and even topological qubits. Each approach has unique advantages and challenges, and the best method has yet to be determined. 5. They require cold temperatures. Many quantum computers must operate at temperatures close to absolute zero, -273 degrees Celsius, colder than outer space, to maintain qubit stability. This makes building and maintaining them incredibly complex and expensive. What quantum computers could offer humanity. Quantum computers are expected to have a profound impact on multiple fields. 1. Medicine and drug discovery. Quantum computers can simulate molecules and chemical reactions at unprecedented accuracy. This could accelerate drug discovery, identify new materials, and even model complex biological processes like protein folding. 2. Cryptography and cybersecurity. Many encryption methods, including RSA, rely on the difficulty of factoring large numbers. Quantum computers running Shor's algorithm could break these codes quickly, forcing a global shift toward quantum-resistant encryption. 3. Artificial intelligence. Quantum computers could revolutionize AI by processing vast data sets and complex models faster than classical computers, improving machine learning, natural language processing, and predictive analytics. 4. Climate modeling. Understanding and predicting climate change requires processing enormous amounts of data. Quantum simulations could improve climate models, helping scientists design better solutions for sustainability and disaster mitigation. 5. Financial modeling. Quantum algorithms can optimize portfolios, assess risk more accurately, and detect market patterns faster than classical methods, potentially transforming the finance industry. 6. Fundamental science. Quantum computers could help answer fundamental questions about the universe, including simulating quantum systems, discovering new particles, and exploring phenomena that are currently beyond human understanding. Why people should understand quantum computing. Even if quantum computers are not yet part of everyday life, understanding them is increasingly important. They will influence how information is secured, how new technologies are developed, and how global industries operate. Awareness of quantum computing can help individuals, businesses, and governments prepare for a future where these machines could impact everyday life, from secure communications to breakthroughs in health and energy. Learning about quantum computing also encourages critical thinking about technology and science. It challenges conventional notions of computing and forces us to explore the intersection of physics, mathematics, and engineering. For students and professionals, knowledge of quantum principles may become a valuable skill, opening doors to careers in emerging technologies. Challenges and the road ahead. Despite its promise, quantum computing is still in its infancy. Building large-scale fault-tolerant quantum computers remains a major challenge. Qubits are prone to errors, and scaling up from tens or hundreds of qubits to thousands or millions requires significant innovation. Researchers are also exploring hybrid approaches, combining classical and quantum computing to maximize the strengths of both. Another challenge is accessibility. Currently, quantum computers are expensive and require specialized infrastructure. However, cloud-based quantum computing platforms, such as IBM Quantum Experience and Microsoft's Azure Quantum, are making it possible for students and researchers to experiment with quantum algorithms remotely. Conclusion: quantum computing represents a profound shift in human understanding and capability. It is not merely an incremental improvement over classical computers, but a radical new way of thinking about information and computation. With its unique properties of superposition, entanglement, and interference, quantum computing promises to revolutionize medicine, finance, artificial intelligence, climate science, and fundamental physics. While challenges remain, the progress made over the past few decades, from theoretical proposals in the 1980s to real quantum processors today, shows that this technology is rapidly moving,